Introduce Dr. Honghan here from Solventum in the health information systems. He's a data scientist there. He graduated, got his PhD from the University of Wisconsin, the Department of Industrial Engineering in 2021. And then he joined 3M, which later Solventum spun out for me. What he's doing in Solventum is highly confidential, so he won't be able to tell you about it here, maybe later in the discussion afterwards. So he's going to tell you about his PhD thesis, and he's going to talk about intelligent sampling strategy for online monitoring of complex systems.
Thank you. Good afternoon, everyone. Thank you for the warm introduction and the invitation again. I'm very honored to have this opportunity to share some of my research on the intelligent sampling strategy to the IMA at the University of Minnesota. So as a professor said, I'm Honghan. I'm currently working as a data scientist at Solventum, formerly 3M. And this research actually was partly sponsored by 3M during my PhD program at UW-Madison. And this research addressed some critical challenges in real-time monitoring, especially in high-dimensional settings. So let's dive in. So here is a roadmap of today's presentation. So I will start with an introduction to the problem and its motivations, and followed by a review of the existing literature. Then I will present two methodologies that we developed. And finally, I will summarize the results and open the floor for questions. So the first example is from the manufacturing processes. So when I was an intern at 3M, I learned that hundreds of the sensors have been deployed in the manufacturing plant to manage different types of data for the quality assurance and also anomaly detection. However, one outstanding question is how could we achieve the optimal balance between the data acquisition and the monitoring performance? So while we can install more sensors and collect more data at a higher speed, the company consistently asks, is that truly necessary? So these questions becomes more critical when we talk about how the sensors could wear out, or we need to change the battery of the sensors, even in the rural areas when the bandwidth is a constraint. So in that case, it is really key that we only collect the most informative data streams that we need. Another application that I quoted here is the solar flare detection, which is an interesting project for NASA. So cameras on the satellites take the picture of the surface of the sun. At each second, tons of the images can be generated. However, due to the limited transmission and the processing time, not all images can be transmitted back to the Earth for the real-time analysis, while those can be reported offline. So the challenging question is that to quickly detect the solar flare occurrences, which most informative data stream we need to transmit back to the Earth at each acquisition time. So in both examples, you can see there is a need of the generic methodology development. So the goal of this research actually is to develop a systematic and scalable adaptive and monitoring strategy that enables us to actively select a partial observable data such that the change detection capability is maximized given the resource constraints. So the main challenges we face includes first, the resource limitations. How to adaptively determine the most informative data stream to observe. And second, the data heterogeneity. So how to design a non-parametric monitoring scheme that accommodates for the diverse characteristics and the distributions of the data. So we aim to address these two issues through the intelligent sampling and monitoring strategies. So our objective is to propose a non-parametric adaptive sampling methods for the real-time monitoring. So these methods should dynamically select the most informative data streams while handling the partial observations and also the heterogeneous data types. So through this talk, I will assume that there are big M data streams in the system, and the measurements of those data are denoted as the XT here. But due to the resource constraint, only small m out of the big M data streams are observable at each acquisition time. And we further assume that when the process is in control, data streams can be heterogeneous, and we have a zero mean and unit variance. So this can be done easily through data standardization. But when the process is out of control, the means for some variables will be shifted to non-zero at some unknown time. And we want to propose a framework that can detect such mean shifts as soon as possible, especially in the high dimensional settings. So the statistical process control, or SPC, has been the foundation for the monitoring the stability and detecting the variations over time. So the SPC traces its roots back to 1920s, when Walter Shorehart, also known as the father of the SPC, introduced the first control chart while he was working at the Bell Telephone Labs. So his works laid the foundation for modern quality control. And by 1950s, new methods like cumulative sum or EWMA charts have been developed. So these advanced techniques were designed to detect a smaller shifts in the process mean. And from 1960s to 80s, multivariate SPC emerged, allowing companies to monitor multiple variables at the same time. And also this time period saw the rise of the Six Sigma and the lean manufacturing, which integrates the SPC into the continuous improvement strategies. And today, SPC has emerged into the real-time monitoring and the predictive analytics empowered by AI and the big data. So the modern SPC not only can do the monitoring the variations, but also can predict the potential failures before they occur. So in the context of our problem, one significant advancement came with the non-parametric Q-sum-based methodology. So you can see the reference here, the Professor Chiu, actually, he was here at the Department of Statistics before, and also Professor Douglas Hawkins. So their method were designed to handle the generic distributions, making them more flexible than traditional parametric approaches. But the central problem is that they require full observations at each acquisition time, which is not applicable for our scenario where we only have partial observations. And as for the adaptive sampling strategy, some methods have been proposed taking the partial observations into consideration. However, the normal distribution or exchangeable distribution on the data and the heuristic imputation procedure in that method are fundamentally not suitable for monitoring the heterogeneous data streams. So another interesting topic related with adaptive sampling is the multi-unbanded problem. So this problem is designed for balancing the trade-off between exploration and exploitation. So suppose that we have 3 slot machines, and we are trying to find an optimal policy for choosing the arm such that the long-term reward is maximized. And to solve this problem, Thompson sampling is an elegant and widely used strategy. It is known for the simplicity and good practical performance. So here is a demonstration of how the Thompson sampling works. So first, we pull the arm machine 0 and observe the reward. And then we update the parameters of the beta distributions here. So you can see M0, the parameters have been updated. Since M1 and M2 are not pulled, so those parameters remain the same. And then we pull a sample from the posterior distributions for each arm, like here. And for the next arm, we will pull the machine tool since it generates the maximum sampled parameter. So by repeating these steps, the Thompson sampling has a capability to identify the best arm, which is a M2 here. And for this application, some researchers has integrated the Thompson sampling into the process monitoring. However, the normal assumptions on the data limits its broader applications. So there is a research gap that we need to propose a method that can handle the partial observations and also the heterogeneous data stream. So that's why we propose the first part of this talk, which we call the AIDS method. So let's move to the proposed methodology. The method we propose to use is a combination of the anti-rank monitoring and the Thompson sampling. So the anti-rank method is a non-parametric method. So the basic idea is that once we receive the measurements xt here, we do a sorting from the smallest to the largest, and we define the first anti-rank indicator to indicate which variables takes the smallest value. So there is a mathematical theorem behind it, and a one-to-one relationship between xt and the causality. So if the distribution of xt changes, then the distribution of the causality will change as well. So that's the reason why this method is powerful to detect the mean shift change, no matter what the distribution the data follows. And we can easily extend this indicator into the last anti-rank indicator. So in this case, we can detect the mean shift change in both positive and negative directions. So let me give you an example of the 4 data streams. So first at T1, we got the measurements, and we know the X1 is the smallest one. Then we assign the 1 to the Kasai one here, and the 0 to others. And for the next one, similarly, we can get the Kasai. And over the time, we can estimate the expectations of the Kasai based on the historical in-control data. So in practice, we can estimate the parameter G here based on the historical data. So when the process is in control, we have the expectations of the causality equals to G. But when the process is out of control, the expectations will not be G anymore. However, when we have partial observations, like I said before, like here, the example, we see the negative 2.8 is the smallest, but there are 3 unobserved variables. So I cannot tell whether this one is indeed the smallest one among all of them. So the central challenge here is that the causality is not well defined. So to address this challenge, we propose to estimate the distributions of the causality based on the partial observations. So we know that the causality follows the categorical distribution with the theta t here. And theta, we can say it's a true time varying parameter. And also the theta t follows Dirichlet distributions of the alpha here. And this is a conjugate prior of the categorical distributions. So the good news is that when we have new observations, assume that we have 4 observations, we have the xt here, then we can update the alpha and get the posterior distributions of the theta. But in reality, we don't have those 4 observations. Like here, the causality, we can get the estimate of the theta based on the in-control parameter G and also the cumulative observations causality. But again, the causality is not well defined because we only have partial observations. So that's why we further proposed an omega to replace this causality, which omega here. So there are three scenarios for the omega here. So when the variable is observed and it's the smallest one among those observed, we assign the probability here. And in the second scenario, when the variable is observed but not the smallest one, then we assign like a probability 0. And for those unobserved data streams, we assign the in-control parameter g here to the omega. So in this case, we can get the estimation of the theta, and also this omega can capture the heterogeneity because it's based on the in-control parameter g here. So with the omega available, actually we can update our first anti-rank indicator, which is the eta here, based on the estimated theta here. So the reason why we use the theta hat, not the g here, is that the theta hat actually is a good estimation of the underlying process, and it's powerful to detect the mean shift when the process is out of control. So far I have talked about the first anti-rank indicator under the partial observations. So next, give an overview of the proposed method. So there are three main steps in this 8th algorithm. First, based on the eta and g, we can construct the Q-sum statistics. So I will not go into details here, but basically we are comparing two statistics, S1 and S2 here. S1 is a local statistic based on the observations with the eta here. And S2 is a statistic based on the in-control probability. So S2 should behave like the expectations of the S1 when the process is in control. And if there are big difference between these two statistics, which means that there is something happening in the process that we need to raise alarm. So that's why in the second step, we construct the monitoring statistic YT here. So this YT essentially is measure the difference between the S1 and the S2. And if the YT is larger than the pre-specified threshold H here, then we will say, okay, the system is out of control. We will stop monitoring and have the QA guys to look into the system. However, if the monitoring statistic is below the threshold, then next time we need to update the sampling layout, which is a third part of this method. So the sampling strategy we proposed is based on the Thompson sampling. So the main idea is to draw a sample Y from the direct distributions with the parameters and is based on is proportional to the local statistic S1 here. So once we got the sample, we can sort the sampled value from the largest to the smallest. And for the next data acquisition, we will choose the top M variables to observe for the next time. So there are two advantages of this sampling strategy. The first one is this random sample will help us facilitate sampling over the heterogeneous variables. So making sure that no matter when and where the shift occurs, we can quickly capture it. And when the process is out of control, a larger value of the S1 can help us to increase the probability to observe those suspicious variables. So here is a demonstration of our proposed method. Suppose we have 6 variables in total, and only 3 variables are observable at each time. So we first acquire observations, then we update the anti-rank indicator based on the observations. And then we can calculate the monitoring statistic right here. And we update the sampling layout. So as the time goes on, the eta will change according to the observations, and the sampling layout will also change. So after T6, there is a mean shift in the first variable x1. As you can see, the eta1 will increase as time goes on, which means that the x1 is more suspicious. And also the monitoring statistic is increasing as well. So through this example, we can see that the proposed method is very responsive to identify the suspicious variables and raise alarm quickly. So in the paper, we also have the following theorem, but due to the time limit, I will not go into details. But the take-home message is that when the process is in control, with the partial observations, the estimator theta hat is an accurate estimator of the underlying process. And the second one is that the proposed sampling strategy can help us explore all the data streams and avoid getting stuck in any data stream. So any questions so far? All good. Okay. So let's look at some simulation results for this method. So first, we investigate how the Bayesian estimation performs. So assume we have in total 6 variables, and we consider 3 different scenarios with different monitoring resources. And this plot shows the estimation of the theta1. So when the process is in control, you can see in the blue line here, the expectations of the eta1 is actually same as the G1 here, which validates our theorem. And also when the process is out of control, we can see the estimation of the theta1 deviates from the G1. And also you can see with the larger value of the M, the distance between these two is getting also larger. And also for the larger magnitude of the mean shift, we can see the bigger deviations from the in control parameter G1 here. And next, we also investigated the explorations and exploitation of our sampling strategy. So to be specific, we calculate the percentage of the time for that each data stream is observed when the process is both in control and out of control. So when the process is in control, under the different monitoring resources, we can see each variable has a sufficient observations. And also the larger the M, the larger the sampling percentage. And also you can see this value actually is proportional to the parameter G here. But when the process is out of control, like here, we introduce a mean shift to the data stream 2. And we can see there is a significant increase of the percentage for the data stream 2, which means our sampling strategy actually is exploiting this data. So for the performance comparison, we can consider to evaluate its method with 3 competing algorithms. So the first one is we call the NAS algorithm. So this method can also do the adaptive sampling with the partial observations, but it assumes that all the data streams to be exchangeable. And the second method is a random sample method. So this method is exactly the same as our method, but with the random sampling strategy instead of our proposed Thompson sampling. So this can show us how much improvement we can make using the proposed sampling strategy. And the last one is a QH01 method. So this one, it assumes that at each acquisition time, 4 observations are available. So it's actually not a fair comparison because it can access more data than what our method can. But comparing this method, we can show how much monitoring capability we sacrifice when we have a limited resource constraint. So regarding the simulation setting, we assume in total we have 50 data streams. And for each method, we consider the same false alarm rate, or we call the in-control average run length to be 370. And we introduce the mean shift differently, like we have a different magnitudes of the mean shift and the different number of the monitoring resources, and also the different number of the shifted data streams here. And we evaluate the performance based on the out of control average run length. So you can consider this one as a detection speed or detection delay. So basically the smaller value of this one, the quicker we can detect those anomalies. So to begin with, we first consider an independent heterogeneous case. So we have 5 different types of the data distributions. And for each type, we have 10 data streams. So in total, we have 50 data streams. And this table shows us the detection delay for each method. Remember, the smaller the value, the better the performance. So you can see as our 8th method performs much better than the other two, the NAS and the random sampling, which shows the advantage of our proposed method. But also you can see the QH01 kind of like has the smallest value here across all the scenarios. This is very expected because this one has a full access to all the data. And this is when we have only one shifted data streams. And the bottom shows when we have a more number of the shifted data streams. So I want to draw your attention for the last row here, the detection of this one and the QH01. So these two values are very comparable in terms of the detection delay. So this is telling us instead of monitoring all the data, all the variables, we can save more than 60% of the resources, but still achieve a satisfactory detection speed. Because in this case, we only have 20 out of the 50 resources available. Another scenarios that we consider is when the data are correlated with each other. And similar trend can be observed. First, this one is our proposed one is better than the NAS and the random sampling. And also for these scenarios, our performance is very comparable to the one with the full observations available. And further, we conduct a case study on the data set of a semiconductor process. So in this case study, we have around 1,300 normal samples, and we consider the 150 data streams. And we only consider 20% of the data stream are observable. And similarly, we have a same false alarm rate, set the in-control average run length to be 370. And this heat map shows the correlations among these 150 data streams. And the right figure shows us the estimated the parameter G here, from which you can see the data is a very high heterogeneous. So this demo will show us how our method works in practice. So here I only plotted some selected variables. So before time 50, the underlying process is in control. So the monitoring statistic is below the red threshold. But after T50, 3 variables are out of control. You can see the monitoring statistic is increasing quickly. And also you can see our method kind of detect this, keep sampling these 3 variables. So in particular, we calculate the percentage of the time for these 3 out of control variables being sampled. So you can see there is a significant increase of this percentage, especially for the X2 and X11 here. So from 6% to 77%. So which means that our sampling strategy capture those out of control variables. So we further compare the method with the next method. So this is a box plot of the average run length on the different observations. We have 20 until 80% of the observability. So based on this box plot, we can see that as the percentage of the observation increases, we can see the mean and the variance of the run length decrease. And also we can see that our eighth method is performing better than the next algorithm, which means we can detect the mean shift quicker than the other one. So to recap, we first propose an algorithm that can handle the partial observations and also the heterogeneous data streams. And also we investigate the theoretical justification of our method. However, there is one limitation for this method, is that when we estimate the parameter g here, we require full historical in-control observations to be available. But this assumption might not hold in practice. So let's say in the military applications, we have UAVs, and those UAVs are dispatched to monitor for the intrusion detection. However, due to the high cost of the UAVs, not all the areas are explored. So if some areas are not explored by the UAVs, the information about those areas is completely lost, and the data cannot be retrieved offline. So in that case, this method will fail to detect scenarios like this one. So that's why for the next part of my work, we propose to address this limitation to relax this assumption and propose a more generic sampling strategy for high-dimensional process. But before that, I want to pause a bit if you have any questions. Okay. So similarly, we have the same objective, but without assuming the full historical in-control data to be available. And we have a same problem formulation and assumptions here. So I will skip this slides quickly. So instead of using the anti-rank based indicator that I talked about before, by comparing the measurements across all data streams, here we construct a quantile-based framework for each data stream separately. So what I mean by that is that this method does not require to cross comparison for all the data streams. And this method only compares the measurements with itself. So we treat each data stream separately. And this method is also non-parametric in the sense we transform the original measurements into a quantile-based indicator. So to construct this indicator, the first step is called a data categorization. So we partition the real line into the small d intervals. And the value of the Q here actually are the boundaries of those intervals. And then we define an indicator y here to indicate which interval the original measurement falls into. So here is an example of 3 variables here. So we partition the real line into 5 intervals here, 2, 3, 4, 5, and we get these boundaries. And for example, at T1, we have 3 different measurements. And based on the definition, we can define the indicator like here to indicate which intervals the data falls. And in practice, we can calculate the value of the Q here based on the sample quantiles of the in-control data stream. But here the challenge is that the y here is valid when we have observations, but the y is not well defined for those unobserved data stream. So how do we define this y when those data streams are not observed? So to address this issue, we adopted like a similar Bayesian framework as before to estimate the distributions of the y. So we know similarly y follows a categorical distribution, and the theta follows a Dirichlet distribution. And when we have a new observations, we can get the posterior distribution, and also we can have the estimator of the theta, which is a theta hat here based on this point estimation. And when the data stream is observed, we can construct the y, and we can update the alpha, and get the posterior distribution, and also get the theta hat here. But when the data stream is not observed, actually we generate a random sample from these categorical distributions with the estimated theta hat as a parameter. So this idea is kind of like a Thompson sampling. We draw a sample to compensate for these unobserved variables. So far we have constructed the indicators for both observed and unobserved data streams, like here. However, there is one issue about such indicators. That is, we lose some ordering information when we transform the original measurements into the indicator. So see the y's here. Actually, the problem is that we don't know which position of the vector where the 1 lies in. So to address this issue, we define the cumulative interval with Ci plus or Ci minus. So specifically, the Ci plus is defined as from each boundaries to the positive infinity. And for the Ci minus is from the negative infinity to those boundaries. And similarly, we can construct the indicator for these cumulative intervals, like here. And based on our simulation, we find out that this A plus is sensitive to detect the positive change, and A minus is sensitive to detect the downward shift change. So by construction of these two indicators, actually we preserve some order informations about the original measurements. Yeah, then based on this A plus, A minus, we can, for each data stream, we can construct a local Q-sum statistic in both directions. So first, let's look at the upward direction. Similar to before, we have A plus, we have a G. We compare the difference between these two values, and we get the W plus for the upward mean shift direction. And here the K is a allowance parameter that will restart the Q-sum if there is no significant evidence of the out of control data. So the larger value of the W plus, which means the more suspicious of the data to be out of control. And then we can update the S plus 1 and S plus 2 depending on whether the data stream is observed or unobserved. Similarly, we can construct another statistic W minus for the downward direction. And since we are interested in both directions, so we take the maximum between these two to form the W statistic. And we do a sorting from the largest local statistic to the smallest one. And the top R, W will be summed up to form the global monitoring statistic. And if this global monitoring statistic is larger than the pre-specified threshold, then we say, oh, this process is out of control. We should look into it. Otherwise, we will just update the sampling layout for the next data acquisition time based on the value of the W. So here is an overview of the method we call the quant method, which is a quantile based and Thompson sampling method. So to begin with, we have incoming data, and if the data stream is observed, we transform into the quantile based indicators. If not, we will generate a sample to compensate for the unobserved data streams. And once we get those quantile-based indicators, we construct the local statistic for both upward and downward directions. And then we form the monitoring statistic. So if it's larger than the threshold, we will raise the alarm. Otherwise, we will update the sampling layout for the next data acquisition. So also we consider another case study for this method. We have around 1,300 normal samples and 100 abnormal samples. And in these scenarios, we have around 400 data streams in total. And this is a heat map for the correlation matrix among these 400 data streams. And also I plotted one PDF for one data stream, which shows that the data is not following normal distributions. And similarly, we have the box plots for the out of control run length under two different scenarios. So this scenario is m equals 20, which is around 5% of the total streams. So we only have 5% of monitoring resources. And this one is around 10%. So as you can see, as m increases, we have more resources, and we can detect the mean shift quicker for each method. But also, you can see there is a significant advantage of our quant method that it's performing way better than the other three one. And this one actually was the first part of my talk. And this is a NAS, so we can see that it's detecting much quicker than the other three. So with that, to recap, for the second part of the talk, we proposed a quantile-based non-parametric QSUM procedure that incorporate the ordering informations to reduce some information loss. And also this method does not require the historical in-control data to be available offline. And also the embedded Thompson sampling actually can help us explore those unobserved data streams for detection. And lastly, we conducted a case study on the semiconductor manufacturing process, which shows a significant advantage of this proposed method. Yeah, with that, I thank you for your attention, and I'm happy to take any questions. Yeah, so actually during the internship, I embedded this proposed method into the data, real data, to detect the anomalies. It's a real manufacturing data. I mean, it depends which method do you compare. So the one I used is like a more traditional, like a statistical process control, but there are other ways that can also to process this data for the anomaly detection, such as like classification. So we can actually, it's basically a classification. So when the process is in control, so you can classify as a 0. If it's out of control, you can classify as a 1. So yeah, people are using different methods to address this one.
So when you compare it to the situation, slower.
I don't remember the results on top of my hand, but yeah.
And currently, so in your current position, you still use the code to develop that.
No, right now I'm switched my directions from this monitoring into the speech recognition. So right now I'm focused on the building the language models. So which is not using this method. Yeah.
But you still, so when you need to deal with someone with this, will you use something that, something based method or you will use very basic, classification of clustering method?
I think from what I know, they are actually using the classification for the detection. Yeah. Yeah.
So in the first part of the talk,
Uh-huh.
you had the chart, you're comparing your method to another method.
Yeah.
You saw like maybe when observation was like 20 or so, you found that your performance was comparable to the state of the art using all of the observation. Did you have any results to quantify that? Like what fraction of your observations to achieve certain performance?
You mean to identify? So let me back up. So when we compare the performance, we don't know which variables had a mean shift. So we evaluate based on the detection delay. So for the first one, if I remember correctly, it's like a 4. So which means so after the mean shift occurs, it takes 4 samples to raise the alarm. But for the full observation, that method it takes like 2 or 3 to raise the alarm. So those two values in a sense are comparable, but we can save up like 60% of the monthly resources because at each data acquisition time, we only observe like 40 of data, like 20. So that's yeah. Does that answer your question? Okay.
And so, yeah, thanks again.
Yeah.
Discussion with students or career
Mhm.
advice.
Okay.
Recording, but you can just